One of the concepts that's going to keep coming up in this class and in other classes is this idea of surface area to volume ratio. So we're going to explore this concept of surface area using these paper cubes. I have two different sizes. You can see that the size is quite different. And then we're also going to compare the surface area to volume ratio of our two cubes with this right cylinder. We're going to pretend it's a right cylinder. So we'll start by calculating the surface area to volume ratio of our large cube. In order to do this, we need to determine the surface area. And all we're going to do is have the length times the width of one of our faces. We're going to multiply that by 6 because that's the number of faces that we have on our cube. So when I do that, I measure about 10 centimeters. So 10 times 10 times 6. That means that our large cube has a surface area of about 600 cubic centimeters. Then we need to figure out the volume, how much space is taken up by this large cube. In order to do that, we need to do the length times the width times the height. And so that's going to be 10 times 10 times 10. And that is our easy math. That means that this space in here is about 1,000 cubic centimeters. The only thing left to do is get the ratio. So we're going to take our surface area, divide it by our volume. Surface area of 600 centimeters divided by the volume of 1,000 centimeters. That means that our surface area to volume ratio for the large cube is 0.6. Now let's calculate the surface area to volume ratio of our small cube so that we can compare it to our large cube. So same thing, what I need to do is figure out the length of one of the sides. This is about 2.8 centimeters. Therefore, length times width times 6 is going to give us a surface area of 47 square centimeters, allowing for rounding error. Similarly, the next thing we need to do is find the volume for our small cube. So length times width times height is 2.8 times 2.8 times 2.8, giving us a volume for our small cube of about 22 cubic centimeters. Then we take our surface area, divide it by our volume in order to get our surface area to volume ratio. We get a surface area to volume ratio of 2.1. So what we can see is that our small cube has lower surface area and smaller volume, but a greater surface area to volume ratio than our large cube. Now we need to get the surface area to volume ratio of our cylinder. The surface area equation of our cylinder is really complicated, but we just need to worry about what the radius is. So what is half of the diameter of the bottom of our marker? And we need to determine the height. So I've already made those measurements. The radius is about 0.6 centimeters and our height is 12 centimeters. So when we put all of this into our equation, we end up with a surface area for our marker of 47.5 centimeters squared. Next up, our volume of our cylinder. Pi times r squared times height. We plug and chug, we put that into our calculator, and we end up with a volume for the cylinder of 13.57 centimeters. Okay, so now we can get that ratio. And what we find out is that the surface area to volume ratio of our cylinder is about 3.5. Now if we go back and compare the volumes of our small cube and our cylinder, we see that they're almost the same, 47 versus 47.5, but our volumes are different. And so even though we have about the same amount of surface area, we have much lower volume. That's going to greatly increase our surface area to volume ratio when all we do is change the shape. So based on the results, we know that even if we keep the shape consistent, having a smaller cell is going to greatly increase our surface area to volume ratio. We can also conclude that given the same amount of surface area, having a roundish shape is going to greatly increase our surface area to volume ratio than being a cube. It's important for cells to maximize their surface area to volume ratio in order to transport substances in and out and around their cells. So if I'm a solute that's in the center of this large cube cell that has our lowest surface area to volume ratio, the amount of distance that needs to be traveled to diffuse out of the cell is much higher than a substance in the middle of this small spherical cell. And we'll look at some organelles that have a really high surface area to volume ratio. So whenever we see something that has a lot of foldings along the surface of an organelle, we're going to assume that that organelle has the function of transporting substances. Remember, form follows function, so if our form is maximizing surface area to volume ratio, that's going to relate to the function, i.e. transporting substances.